start, some quick announcements. First, please do make sure you're muted if you aren't already. And second, put any questions that you have in the chat. As with the previous sessions, I'll be moderating and we'll be sending the questions along afterwards. So without any further ado, I'm really excited to introduce Daryl DeFord from Washington State University, who's going to be talking to us about how to use Python for networks. Please take it away, Daryl.
Thanks. I'm really excited to be here talking to all of you. So thanks for coming and showing up today. My role is, oh no. Well, there's, sorry, that was not the technical difficulties I was expecting, but hopefully I'll at least stay visible for the rest of the talk here. So my role is sort of to follow up on Heather's awesome talk and sort of walk through some of the ways to compute some of the quantities that she talked about, talk about how to sort of import graphs and networks into Python, how to work with them, what sort of objects there are. We've got a really broad sort of collection of backgrounds for people in this audience today, starting from people with no programming experience to people who have much more programming experience than I do. And so this talk is really not particularly tailored for anyone, but I am hopeful that it will have sort of useful information for everyone as part of the material we're going to cover. So just a brief introduction to my experience. I got hooked on studying networks in graduate school, ended up writing my thesis about sort of dynamics on complex networks. And then worked as a postdoc a couple years, really focused on questions about gerrymandering. How do you build sort of software tools to sample districting plans and to detect gerrymandering and sort of inform reform efforts? And a lot of that work sort of worked directly with Python and generating packages to build on top of the NetworkX class that we're going to talk about today. So the main outline that I want to cover is to talk a little bit about how Jupyter networks work, how Python works a little bit. Talk some about how to work with small networks in Python. So we'll talk about ego graphs, what some of the sort of just starting points is for you to get some experience. And then we'll sort of dive in and look at some larger social networks, some ways to import those, ways to compute some of the metrics that Heather talked about, look at visualizing centrality and those sorts of things. And then wrap up at the end with a little bit of discussion about dynamics on networks, how to sort of implement those in Python and NetworkX, and sort of how those can be visualized nicely as well. So throughout this talk, what I'm going to do is just start and show you some slides, give you a brief overview, refresher of a couple of things that you saw just half an hour ago in Heather's talk. And then we're going to walk through some of these notebooks. And so those are available online. They're linked through the course webpage as well as on GitHub. And so those have some expository text, they have some code examples, and they also have some example assignments for you to play around with to try to, if you're interested, later on, to sort of extend the things that are presented there and try them out on things that are interested to you. And so in particular, I'm going to show some examples of the syntax, and also, part of the reason I selected some of these examples is there are a few things that are really natural to want to do, like some of the spectral partitioning that Heather talked about, that are kind of a pain to implement in Python particularly. And so I've provided implementations of those to give you a starting point for some of these things, so you can really jump right in and start doing some of the analysis. Additionally, when we put these slides up online, these got some links here to some additional resources beyond what I'm going to talk about today. So some of those are contained on GitHub and the short course webpage. As we'll see throughout the notebooks, there's a bunch of links to sort of the primary source material and some extra exposition about some of the mathematics underlying the ideas throughout those. We'll also take a look at the NetworkX documentation just briefly. It's a really nice example of one reason to sort of prefer this approach to studying networks is they do a good job of giving not just code examples, but also citations to the underlying mathematical papers so you can go read about the ideas that they've implemented. And finally, I've got some links here. People over Slack reached out a little bit and were interested in places where they could start playing with some network data. And so these links will take you to some examples of various sizes to start working. So to start out, like I said, I just wanted to give a brief overview of some of the ideas that we're going to be talking about. And so in particular, so Heather gave us some nice examples of penguin networks. I wanted to talk about a little bit about otter networks, so very small social networks of otters in zoos. As a good example of, a lot of times these days we think a lot about giant networks and wanting to have billion node Facebook graphs, but there's a lot of really interesting and impactful analysis that can be done at a much sort of smaller scale. And so we'll start there talking about how to build some of these small networks in Python using an example of ego networks. So this is an idea that sort of grows out of sociology, and over the last decade has become sort of something that people have been interested in, again, thinking about snowball sampling and things like that. And the idea is we're just going to have a network that's going to start with some sort of central individual, sort of the ego, and then we're going to sort of capture who all of their friends are in our network and look at the connections between those friends as well. So I've got an example here of my ego network, say of just a few nodes. You notice that I'm not connected to one of the cats because I didn't give her snacks this morning. So this isn't a perfect ego network because one of those fundamental friendship links between the center node and one of the other nodes is broken down. But we'll want to look at sort of smaller things like this just to get a sense of kind of local social structures and some of their important properties. This also relates sort of really nicely to some of the generative models that Heather talked about. So one of the really interesting questions you can think about is we have these different generative stories, ways to think about how networks grow, what their sort of important properties are. And an interesting question to think about if you go through and sort of build your ego network, and we'll look at how to do that in a second, you might think about which of those known models could reproduce your network. Are there sort of ones that have the right structure? Are there ones that don't? Which ones are sort of most naturally capture the types of connections that led to your ego network? And these are sort of really natural types of questions to think about that make sense on a small scale as well as a large one. After we do that, we're going to hop over and look at some larger social networks, like I said. And so, Heather mentioned several features of social networks that are sort of distinct and sort of common that we see over and over again. Gave us this example of the Karate Club network down at the bottom. And so, things like, triangles being likely to close up, the likelihood of community structure, some of these sort of small degrees of separation across the networks. And so what we'll look at is ways to A, sort of measure these quantities on networks, and B, an example of sort of comparing the quantities from real world networks to some of these generative models that are matched some of the parameters to the social networks. And then we're going to wrap up, hopefully, by looking at some examples of dynamics. So Heather again mentioned sort of the Laplacian and heat flow and diffusion through networks. An example that came up yesterday was these SIR models, which are sort of unfortunately at the forefront of everybody's mind these days. And so I'll provide sort of a notebook and some code to look through those and sort of start experimenting with what happens as you change the underlying topology, what happens as you change some of the parameters of the model to sort of the outputs of the data dynamics that we're looking at. So that's sort of the roadmap for where we're going. So we'll hop over now and take a look first at some of just what the documentation looks like, and then start playing with the notebooks themselves. So this is the NetworkX documentation. And one of the things that I'm hoping to sort of prime you for, again, given the sort of range of backgrounds that we have here, is not necessarily like leaving this 1 hour session with the knowledge of exactly the right way to do anything that you want in terms of computing things on networks, but definitely the knowledge of where to start looking, whether that's copy and pasting some of the code out of the notebooks, looking at the documentation or some of the other sources to try to understand what the right sort of starting points are to do the analyses that you're interested in. So as I mentioned, one of the nice things about the NetworkX documentation is that beyond being sort of complete, it actually does do a nice job of talking through some of the actual sort of academic references. And this is true not just in general, but also for the sort of individual algorithms. So if we go look, say, at the centrality calculations, like Heather talked about a little bit, if we want to know about eigenvector centrality, it not only sort of provides us with the technical information, what does a code example look like, how can we make this work, but also sort of goes through some notes, provides references, talks about some of the underlying theory. And so as mathematicians, this is one of the things that frequently makes us happy if we can sort of have a little bit of context and broader information to follow along with, rather than just, here's the code snippet and it works. So this is always a good source to come back to, and it's linked in different sections throughout the notebooks. So I mentioned that the notebooks here are up on GitHub. And if I could pull up the chat window, I would put in the URL for you to follow along here. But I apparently can't, sorry. But it is available on the Slack channel. And so if you want to sort of follow along with the things that I'm going to talk about here, I'm going to sort of just go in order here, 0, 1, 2, and 3 through the notebooks. And so if you want to just sort of click on one of those, then it should sort of load the content for you, and you can see both the exposition and the code snippets. So if you load these directly on GitHub like this, you won't be able to sort of modify the code on your own. You'll need to either sort of open them in Colab or get a Python installation on your own computer, but you will at least be able to sort of follow along with the content that I'm going to talk about. So I think I'll pause just briefly here before we go and look at this first notebook and see if there's any questions that I should address right now.
I think we are good.
Great, okay. Perfect. So this is sort of an example of the Jupyter Notebook setup, and it's organized into sort of two types of objects. There's some of these sort of text examples that sort of tell you hopefully useful facts about the rest of the cells. And then there's these sort of ones that say sort of in to the left of them. And when you evaluate those sort of pass whatever you've put into the cell there over to Python and asks it to evaluate. And so if you're sitting here facing this, you can evaluate individual cells by holding down the shift key and clicking enter. And so it'll run that there, or you can click this little run button up at the top. And so we can sort of, change the arithmetic a little bit here. It does shockingly know that 2 + 3 is 5, which is good. It knows things about the order of operations. You can use parentheses to do basic arithmetic. That sort of setup. We're going to need just a few basic ideas from here. So hopefully, if you're sort of new to Python, new to Jupyter, I do recommend sort of reading through the steps here just to get some basic background. Something we're going to use a lot is the idea of variables. So we're going to assign, say, a graph to a name that we're going to use to reference it later on. You can do sort of arithmetic with variables, sort of as you normally expect. So here we've set a to be 5, and sure enough, a + 2 is 7. If we change a to be 12, then later on, if we add 2 to it, we get 14. So there's a persistence of variables throughout the notebook, which is something we're going to sort of make use of throughout cells. You can sort of have multiple lines of code included in a single cell. They don't all have to be sort of individually separate lines like this. And if you do that, Python will sort of evaluate all of those cells sequentially, sort of from top to bottom. If you notice here, sort of throughout the text around the cells, I've included just some assignments for you to think about. If you're interested in trying things out on your own, change some of the numbers, try to tweak things a little bit, see how it changes the output to get just a little bit of experience and sense for what it's like to work with these objects. There's no need to do that right now or anything, but if you are sort of interested in doing a little more of these later on, these will sort of guide you through the experience of what it's like to work in these Jupyter notebooks. Something that's likely to come up as you start to do some of that modification and things like that is that you're going to get some error messages like this. This is a fundamental part of programming, is making mistakes. And so there's nothing wrong with that. It's totally normal. I'm sure that I'm going to generate more than one error in the rest of the talk today. It gives you some sort of helpful text, hopefully, to help sort of diagnose what's gone wrong. But the important thing is not to worry about it and to try to go back and change things, try to understand what went wrong in the text that caused the error itself. There's some other description of some of the data types and data structures here that you can look at. I'll talk later on when we get to some of those individual parts for the graph specifically about those, but just some extra context there. And then finally, something that I want to point out is that Python itself doesn't have support for graphs. That's why we need this network X package. And so in the rest of the notebooks that we look at, we're going to sort of import that at the top of the notebook so that we have access to the graph class and sort of the network metric functions that we want. So here, this is just showing an example of what that syntax looks like. We're importing this randint function, which generates a random integer. And the last thing that I wanted to highlight about that is if there is any randomness in the process, that's going to change as you sort of rerun the notebook. So here we're just sort of sequentially as we rerun this cell, drawing new random integers between 0 and 20. And we'll see some example of this later on when we apply some of these generative models. See, we'll get sort of different networks every time we rerun the script. And so finally, down at the bottom, there's a link to some extra information in a textbook, as well as a couple of keynote speeches that are each an hour long about sort of the uses of notebooks in sort of research and pedagogy, taking sort of different perspectives on whether or not they like them. So we have I don't like notebooks from 3 or 4 years ago, and then I like notebooks from last year, sort of providing some extra information about the ways that these actually do get used in practice for both sort of researchers and teachers, people who are trying to communicate ideas in data science. So are there any questions about that before we actually sort of move on and go look at some networks in Python? I know that was a very fast sort of zoom through.
One really quick setup question that maybe you can answer because I can't. What would cause a JSON error? I'm getting this message when trying to open the second Jupyter notebook, unreadable notebook, does not appear to be JSON.
Oh, so did you sort of like download it and copy and paste it like into a text file or something?
It appears to be a local file based on what is in the message.
Yeah, so what happens, let's see if this is kind of a thing to pull up. So these notebooks as files themselves are sort of stored as JSONs themselves. So you need the .ipynb extension to open them in the Python notebook. But if you just open them in a raw text editor, they'll look like kind of a raw JSON file. So usually you can just, if you're opening it with the Jupyter interface, so something like this, you should just be able to open them directly, like if you launch Jupyter Notebook from your terminal.
Awesome. Hopefully that will work.
Yeah, and if not, definitely shoot me a message over Slack later and we'll get it figured out.
I think the other questions can be held till the end of the talk.
Okay, great. So now let's actually like take a look at this and actually do some work with networks in Python. So like I said, this is the for number 1. I guess I started 0 indexed here with the notebooks. And so our top Python line, we're importing this network X package, and that's what we're going to want to do to actually build the graphs. And so we're going to start small. We're going to build up one of these ego networks. And by sort of adding individual nodes and edges to the graph. So this is something that works at scale for things like otters or penguins or ego networks, not something we'd want to do for the larger scale networks. Even typing these in individually for the Karate Club would be a pain. And so we'll see in the next notebook sort of how to. But for now, we're going to start off and just make an empty graph here. And so we do that. I'm going to call it my ego graph. Make things clear, use this variable assignment equal sign, and then this nx.G graph is going to be our starting point. So right now, this is a graph with no nodes or edges. So this is a mathematically appealing empty graph. Right? And we're going to start just by adding individual nodes. So since this is my ego graph, I'm going to take that variable and use this .add_node function to add a node for me. So now we've got one node in our graph. We could sort of continue adding the nodes individually like this. So we could add extra lines under this one, my ego graph, etc. Type in somebody else. We can also add in nodes from a list. So we can add in a bunch of nodes at once. So here I'm going to add my wife and our 2 cats. So now our graph has added me, and it's added 3 of my initial connections here. Just like the add node syntax, there's an add edge syntax. So we're going to start and put an edge between my wife and I, an edge between me and one of the cats who got snacks this morning. And then we're also going to add some more edges. Now I'm going to add my parents and siblings in. Notice that here we didn't add the parents and siblings as nodes to start with. And so that's completely fine. And when we ask it to add this edge between a node that's in our graph and a node that's not in our graph, it's just going to add an extra node from that endpoint. So now we've got, I think, 6 nodes in here. The one we added initially, the 3 we added together, and then 2 more nodes that we added by adding edges to them. Just like the add nodes from structure, there's also an add edges from structure. So we'll put the rest of the edges in there all together, just in a list set off with square brackets here. Okay. So we can add individual edges, add collections of edges, add individual nodes, add collections of nodes. And now if we want to see sort of what are the nodes that we added into our graph, we can use this sort of dot nodes function, and it gives us this nice list of me, my wife, 2 cats, parents, and siblings. So those are the nodes in my ego network to start with here. And we can also get the edges, and we can see that all of those ones that we sort of added individually are here to look at. So in some sense, we've sort of represented our whole graph, but trying to look at it just from these sort of ordered pairs of edges is kind of a little bit inefficient. And so instead, what we'd like to do is sort of visualize the structure. We'd like to try to understand what does this ego network sort of now look like. And so the main function for drawing networks is this nx.draw function. We're going to use this a ton over the next 3 notebooks. You know, again, there's a link here in the notebook to the documentation that sort of walks through all of the possible parameters that you can use to set the, you know, change the look of the graph. And we're going to play with a bunch of those throughout these notebooks. So to start out, if we just ask it to draw the ego network, what we get is this sort of nice small graph in the middle of the page here. And so in this case, it would be nice to know sort of what the nodes were actually named. We'd like to have some understanding of what the individuals in the network are. So we could do that with this sort of with labels command and sort of add names to the nodes. Also made the node sizes a little bigger so that the labels would sort of fit inside the nodes that are displayed there. This is one really funny sort of parameter of the NetworkX sort of drawing family. The default node size is 200. And so if you're sort of starting to think about how you want to scale these to fit labels or to fit together when you have larger graphs, you know, setting it to be 100 is actually half the size of the normal nodes that get drawn. So you have to sort of scale up your mind a little bit there. So 100 is usually too small for small networks like this. We want something that's a little bigger so that we can see the individual nodes. Just like setting the sizes, we might want to sort of change the colors behind things. So here I've changed it to gray. You know, lots of options here. You know, most colors that you can sort of think of are included by default here. So you sort of pick your favorite color scheme. A lot of times later on, we're going to want to color, say, maybe all the nodes differently to represent some feature or property of the graph, maybe sort of scale them by a centrality score or a community assignment, like in the Karate Club. And so both the node size function that we looked at and this node color function can instead take lists of arguments, and it sort of will associate those colors with the individual nodes here. So I got turned red, Katie got turned blue, cat number 2 got turned green, and so on. And so the ordering here, if you look at these nodes, is actually exactly the same as the ordering that we had when we asked it to print the list of nodes that we started with. And so later on, what we'll do is we'll sort of use this in a more automatic fashion to sort of build long lists of colors or you know, scaling variables that can make sort of color schemes work across all of the nodes without having to sort of type in individually what we'd like for each node. You know, we can also do things like change the shape of the nodes. So here we've changed them to be squares instead of circles. And like I said, that documentation link up above will tell you sort of all sorts of different ways that you can modify the underlying graphs. Okay. So you notice there's another sort of, oops, assignment text here, if you want to sort of go back, replace me with yourself and sort of build some additional examples, build your own ego network and make some colors out of it. One thing that I should have pointed out before is that if you'd like to, so the starting point for this was all the way up here. If you'd like to add some cells to do your own work instead of working inside the ones that are presented here, you can click this insert button at the top and do something like insert cell below, and then you could start building your ego network, starting with an empty graph and adding some nodes to it if you'd like to tackle that assignment. The last thing that I want to point out about these ego networks is then one of the really nice features of Network X as a package is that it also allows us to sort of associate arbitrary labels and content to our nodes and edges. So one of the things that we'll probably like to do later on when we talk about dynamics is, say, if we're thinking about an SIR model, we might want to have a health feature attached to each of our nodes that says, which of the categories are you in? We might also want to have sort of numerical features. So for example, we'll look at some of the data that underlies some of this gerrymandering work where each sort of node represents a unit, like a precinct or a county, and we'd like to know how many people live there and how many people in the last election voted for each party there. And so you can set these parameters on the nodes by using this sort of square bracket syntax. So here's our same ego graph that we built above. And then we use the .nodes function. And here we're adding an age parameter to me in this case. And so we started out, there wasn't anything associated to my name in the graph. I didn't have any sort of attributes. Now we've added an age attribute. And so if we ask the graph again, what are the attributes associated to Daryl? It says there's an age there. We could also do this for the color. One of the assignments at the bottom here that you can take a look at asks you to think about how to do that for all of the nodes. And as we add these attributes, we just sort of get to be a larger and larger sort of collection of information about each of the nodes in the graph. And so here I've gone through and added sort of the ages of everybody in the ego network, taking averages where necessary to represent multiple people. And so now we've got sort of an age column associated to each of our nodes. We can also add information to edges. So here I've just added a length column to one of the edges in the graph. And so now if we ask sort of what are the properties of my node, then it says, well, along this edge, we've added this one annotation. There aren't any other annotations on the edges. And so then this next block, what it's doing is it's saying, okay, we're going to iterate over all of those edges. And we're going to add this new label called age difference, where we just sort of subtract the age of each of the nodes, right? So we added an age to each of the nodes. Now we're going to take the absolute value of the difference between them just to get sort of a funny label on the edges. And again, now if we ask for the information about the edges, we've got an age difference across all of them. And so we can use this type of information in the plotting as well, right? So we can make sort of the edges wider. So here the node sizes are scaled by the age of each person, and the edge widths are scaled by the age difference between them. Probably not like a really meaningful notion of connection in a graph, but does just sort of provide an example of how to sort of incorporate those types of information. And so you can see here, instead of just having a fixed node size, we're instead setting the sort of size of the node to be 100 times the age of each node, right? This is where that scaling comes into play. If we didn't have that 100 times, then the fact that the default is 200 means that everybody is way smaller than they a little hard to read. Great. And so I do, if you have sort of a quiet Sunday afternoon coming up or at some point, I do recommend sort of going through this process, looking at some of these assignments, trying to change some of these labels, picking your favorite colors and doing that sort of. So are there any questions about this before we sort of move on to looking at some larger graphs? Definitely a lot to sort of play with and work with.
So there's been some discussion of this in the chat already, but you may also have some insights that we haven't had. Can you talk a little bit about like the layouts for the graphs and what different kinds of layouts there are?
We are getting exactly there. Yeah. So something that probably some of you noticed, and if the Zoom toolbar ever goes away, there we go, is that as we sort of plotted these graphs, the sort of orientations changed as we did them. And so maybe we'd like to have a consistent orientation show up so that we can sort of see the same embedding over and over again, particularly if we're going to do things like compare sizes or colors as we sort of change those to mean different facets of the graph. So yeah, we're going to get there in about a third of a notebook. So to start with, so I mentioned, we normally, for sort of reasonably scaled graph problems, don't want to actually build our networks by hand by adding each individual node and edge into the graph. And so I'm going to look at a few different ways to sort of bring larger graphs into Network X to work with. As Heather mentioned in her talk, like sadly, if we're just getting sort of data from arbitrary sources around the internet, there's very little standardization about the formats that those might come in. So I've provided examples here of a couple of different ones, as well as sort of a pointer to the documentation that shows you how to handle something like 62 different formats or something. But it can be sort of a little complicated to do that. To start out with, there are some sort of graph families that are included in Network X to begin with. Sort of these are called graph generators, and there's a link to the documentation here. And so this is our nicest case. If the graph that we want is part of a family or is a graph that Network X already knows about, then we can just sort of ask for it. So here, for example, we can't give a graph theory flavored talk without having the Peterson graph. Sure enough, Network X knows about that one already. And so here's what that looks like. Similarly, a lot of times we might want to work with grid graphs or lattices as a place to start. And, so there's a sort of support for that. Here, the number of sort of rows and columns in the graph are what we get. And you notice, and so this was just what was brought up, it's sort of awkward that if we ask it to plot some of these graphs, like there might be a really natural embedding that it's really missing out on, like, topologically, fine, this is the right graph, but visually it's not conveying a ton of useful information. And so the way to sort of handle that is through this optional sort of POS, which stands for position argument to the draw function. And so here's the small graph again. And you notice in this case, the nodes are actually named with a position of the vertex. Here, so 0, 0, 0, 1, 1, 0, all the way up to 4, 2. And so what we're going to do for this graph is we're just going to make a little dictionary here that maps the name of the graph to itself. So it's just this ordered pair of positions, and then we're going to have it plot the nodes at those positions. And so here, now we're going to get the same layout every time of the graph. And so this sort of syntax is exactly what that position argument wants. So it wants a dictionary that maps the name of the node to an ordered pair, sort of in the Cartesian plane, where to put that node. And so again, most of the time we won't be so lucky that the name of the node is exactly where we want to place it. And so in a second, when we look at the social networks, I'll show you some of the different layout options that there are to sort of extract these position vectors automatically. So there is this long list of sort of combinatorial examples of graphs in Network X. There's also constructors for all of the random graph families that Heather talked about, along with the parameters. So here we're building sort of this Erdős-Renyi graph, where we've got this sort of just random independent edges between all of the nodes. Similarly, for the preferential attachment graph, with the same parameters that Heather talked about. And here's that sort of Watts-Strogatz graph again, nodes, size of the sort of connections initially, and this rewiring parameter, just the same as we saw before. And like I mentioned with the sort of the randomness, so here for these generative models that are drawing samples from this distribution, if we rerun these, we're going to get a different graph. So it's asking, it's redoing that entire random process. There also are some social network examples in addition to sort of the random networks and the combinatorial families. And so in particular, one that Heather talked about was this karate graph, which is there automatically. An x.karate graph will give us that graph to work with. And if we look at its nodes, they're just indexed 0 through 33. So we just have no names like we had in the ego graph, just sort of integer indices. And there is a little bit of information on the graph. In particular, after the club split, did they go with the original sensei, or did they go with the president of the university club? And so each node has a label that says what they did after the split. So I think, yeah, go up far enough, we'll find some of the nodes that went into the other half. And so here's an example. Now we're going to sort of plot the karate graph, and we're going to color the nodes, in this case, by the assignment. Were they in the club with Mr. High? Did they stay with him, or did they move over to the new club formed by the officer? And you can see this sort of nice example of partitioning that we saw in Heather's slides. And so now I want to sort of directly address that question. So if we're going to, about layouts, if we're going to sort of look at these graphs over and over again, if we want to maybe look at sort of different clusterings on the same graph, it's much easier for us to sort of gain intuition if we can sort of lay out the nodes in the same way. So we can do that by sort of extracting layouts for an individual graph. So these are functions here provided by NetworkX that are just going to output these sort of Cartesian coordinates of the nodes according to some collection of algorithms. So I've got some examples here that you can play around with. Kamada Kawaii, layout in a circle. This random layout just picks random points in the unit square and associates the node to those. The spectral layout uses the Laplacian and an embedding based on those to do the placement. And so the outputs of these are exactly like I said, mappings of the node names, which are just these integers, to these sort of pairs of Cartesian coordinates where to place them. And so while when we did just the regular draw function, we sort of got different layouts every time we run the cell. Now we can sort of just use this POS command with one of these layouts, and we're always going to get exactly the same layout. So here's the Kamada Kawaii layout, and here's what the sort of circular layout looks like, just numbered by the individual node labels as you sort of go around the circle. All right, so what if we're not so lucky? What if NetworkX doesn't know about our graph initially? So there's a whole bunch of ways to sort of store graph information, whether it's adjacency matrices, adjacency lists, various sort of proprietary formats. The example that I'm sort of showing here is what if we have one of these big adjacency matrices? So we can sort of painstakingly type in all of the zeros and ones to the notebook and include them. It's usually not sort of the sort of best practice, but I did want to just show an example. If you have an adjacency matrix, then this is sort of the syntax to get the network out of it. If you look back to the GitHub page, also included just the same dolphin graph in a CSV file, and we can also just load those in directly. So again, this is one of those things that's sort of a pain if you don't have the syntax at hand, but in just a few lines, we can sort of extract this just out of any CSV that just has this 0 and 1 adjacency information and get exactly the same dolphin network out that we did for typing the whole adjacency matrix. Another sort of really common format for storing networks these days is the Json format. So this is something that in particular gets used a lot when you have a lot of annotations on the nodes, if you have a lot of extra information associated to the network, not just the adjacency structure. And so again, I have an example of the syntax here and uploaded just an example JSON graph. So you could play with it a little bit. This is the sort of dual graph to the counties of the state of Arkansas. I don't know if we have anybody from Arkansas here today. But this is my favorite county dual graph out of all of them. So now I'm inflicting it on you guys. And so you can see that I've here just listed sort of all of the information that's contained on those graphs. You can see that like this would be sort of a large pain to sort of type in manually, but the JSON format makes it sort of efficient to store. And so we have some geographic information where sort of the lat long coordinates, what's the sort of population for the nodes, how does that break down between the urban and rural populations, and then a bunch of sort of demographic information provided by the census. And so here, I'm just sort of drawing that same graph. Now here we're sort of coloring the nodes by their total population, right? And so you can see you've got a few sort of very well populated nodes, much larger populations than the rest of them. And it sort of breaks the scaling a little bit here. Here's another example of, in this case, we changed the size of the nodes are proportional to their populations. but the colors are sort of proportional to whether or not the population is mostly urban or mostly rural. And so unsurprisingly, you get sort of these large nodes that are very urban, lots of people live there. The smaller nodes tend to be rural, so much less sort of land mass in those examples. I've also just got an example here. So here, these files were uploaded directly. They were in the directory where we were working in to load them in. You also can sort of use Python to just go track down networks across the internet and load them automatically. So again, this is sort of a pain to do, to work out for yourself, but it is an example of the syntax. I've got all of the census networks at sort of all of the levels across the country stored on the internet somewhere. And so you can just sort of download them automatically by changing this sort of string label up here. There's a description of the full data set at this link in the notebook. And you go look and see sort of all the information on those. So here, we have the counties of Florida. It's an exciting graph to work with. There's other sort of units. So I think there's also, look at, say, census tracts of Florida if you want. That'll take a minute to go download it because it's a larger network. But so some of the sources, if you look back to the slides of places where there was information about the individual networks and data sets, you can sort of load those in automatically without actually having to download the file separately. There's a lot more nodes here, so maybe this node size isn't quite right. Maybe we want to sort of shrink that down a little bit, see if we can get a little better resolution. Still a lot of nodes. Okay, there's 4. And so hopefully, again, this is one of the places where this is a great place to think about sort of copy and pasting this code for your own use later on, not having to sort of work out how to sort of load these things in if you do have data that shows up in a weird format. And so now I want to talk a little bit about how do we actually measure these metrics that we talked about for networks. So Heather gave a bunch of examples of some of the types of things about paths, about centrality, about triangles and clustering in the network that we might want to look at. And just with the things we talked about previously, the documentation for the algorithms here walks through a big collection of those. So if you're like, I'd really like to measure, some sort of obscure metric on my graph that I have, it's usually a reasonable place to start is, looking through that documentation, seeing if there's a function for that already. So I'm going to walk through this with just that karate graph example because we already sort of loaded it in here. And so some of the functions we can just apply to the karate graph variable directly. So the order gives us the number of nodes. Sure enough, there are 34 of them. The size gives us the number of edges. And sure enough, there are 78 of those. Heather talked a little bit about the diameter and the radius of the graph, so these path length based measures. And so the sort of more common syntax here is that there's a function associated with the network X package, so in this case diameter, and we feed the karate graph into it as a parameter that it gets evaluated. So same for radius, so diameter is 5, radius is 3. Average shortest path length, so this measure across all of the shortest pairs in the graph. The name of the function is average shortest path length. So as long as you spell all the words right, it's usually, I won't tell you how many times I got that wrong on this slide, just trying to make it, but the syntax at least is sort of interpretable. And similarly, some of these transitivity and clustering coefficient measures what proportion of triangles in the graph close up. For example, how many triangles are there in total? And so if there are metrics you're interested in, then usually it's just a question of finding the right function to evaluate on your graph to get a starting point for analyzing some of these ideas. The triangles function itself actually returns something that's a little funny. So it returns a mapping that maps each node to the number of triangles that that node participates in, or is a part of. And so as we'll see, this is actually something that it makes sense when we're trying to sort of color and scale the sizes of the nodes by some quantity. So for example, here I'm using that same draw function, the same layout, so we can look at them all in the same order. And here the nodes are colored by the number of triangles that they belong to. So dark red for lots of triangles, yellow for a few triangles, and then blues for not very many triangles. And that uses sort of exactly this mapping, this information of how many triangles they belong to. you can sort of see, you know, here the people who seem to be sort of most the hubs of this sort of small network, you seem to lie on more triangles than anybody else does. The syntax setup for the centrality measures is the same as these other metrics we talked about, and they return something that looks sort of exactly the same as this triangles count. So just briefly, Heather showed you sort of definitions for degree centrality, eigenvector centrality, closeness and betweenness centralities. And so if we just apply that to the same Karate Club network, then the output is again this sort of mapping of nodes to their score under that particular metric. And so here now in the notebook, I've sort of scaled each of the nodes both in size and color by the corresponding centrality measure. So in this case, we've got the nodes sort of scaled by their degree, their number of friends. The next one, we have it sort of scaled by the eigenvector centrality, so this sort of recursive definition. And this is a place where exactly that question about how do we get these layouts to work consistently makes a big difference. Now we can sort of compare visually these networks to each other, try to understand the differences, what the various centrality measures are telling us about sort of the types of importance that they're about the network. And so in here, you can also see the closeness and betweenness examples. The assignment asks you to sort of go through and do this for the Dolphins network as well, see what you sort of observe about the differences. And then the final set of examples in this notebook walks through this question of how do you compare some of these social networks to, say, some of these random network models. So, you know, we talked about networks having sort of high clustering, but high clustering compared to what? And so the example that's actually in here takes the karate graph, and it builds 100 Erdős-Rényi networks that have the same number of nodes and, at least in expected value, the same number of edges as the karate network that we started with, and measures a few of these network statistics. So the number of edges, this transitivity score of closing of triangles, actually the number of triangles itself, and this average path length. And then down below sort of makes these comparisons. So I compared to the 100 number of edges values that we saw, the Karate Club lies right in the center of the distribution, which makes sense because these networks were drawn to have that as the expected value. I feel like we've done sort of the right thing there, hopefully. But if we compare the transitivities, we'll notice that there's sort of much more clustering happening in the karate network than we saw in any of the Erdős-Rényi graphs. And this makes sense since the edges in the Erdős-Rényi graph are independent. We sort of expect them to not display clustering. And so this tells us there's something interesting happening in the Karate Club graph. It is one of these social networks. There's something driving the formation behavior that's different than just everybody sort of walked into the club one day and flipped coins with each other to decide who would be friends. So we can do these sorts of comparisons with sort of all of the metrics, including you know, the average path length, or comparing the sort of degree histograms that Heather talked about a little bit for these examples. And so I guess before we go on to the last notebook, are there any questions about this setup? And I know like we zoomed through a lot of content here, but hopefully the main ideas and the places to look are coming through.
One question, sorry, let me scroll to it. How does Network X decide how many colors to use when you're specifying a color by node property?
Oh yeah, that's a really great question. So what's happening here is we have like numerical scores for the various nodes. And so it has what's called a color map. So at the end of each of these, it gives you this option of what you'd like to use to change the gradient between the color schemes. And there's something like, like 85 or so different color maps. And inside the notebook here is a link to the documentation that shows all of those choices. And so every node gets in this case, I think they all have different scores. So they each get a unique color that lies along this gradient that's just normalized from 0. Great question. Cool. So then at the very end here, I just want to look through a couple of, the chat finally showed up. A couple of brief examples about sort of dynamics. So this is a thing that sort of mathematicians really like to think about networks, right? It's very natural to say, well, I want to associate a value to every node or every edge and then let that evolve under some sort of operator. There's a lot of sort of really natural mathematical questions that direction. And so this final notebook walks through three sort of key examples of that people like to study in the context of complex networks. So those are sort of random walks on graphs, so like the simple random walk where you imagine your Markov chain represents a walker who visits the nodes of the graph and at every step chooses one of the neighbors uniformly to hop to. You might be interested in things like how long it takes that walker to sort of be lost enough, right? So thinking about things like the mixing time, whether there are obstructions in the graph to being able to move around effectively, what the sort of steady state looks like for the Markov chain. One that came up in Heather's talk as well is the idea of diffusion as governed by the sort of graph Laplacian, so as a sort of linear differential equation applied to this vector of values assigned to the nodes of the graph. And then finally, this idea of sort of epidemic spreading. So, you know, a lot of times the SIR model gets formulated in sort of a continuous fashion, but it can also be sort of formulated and evaluated in a discrete fashion, where we imagine that each sort of individual in the social network has some status, either susceptible, infected, or recovered, and they have some probability, if they're infected, of infecting their susceptible neighbors at every time step. And so the examples here sort of walk through ways to implement each of these using exactly this kind of annotation information that I talked about a little bit in the ego network section. So, you know, for example, we can keep track of the position of the random walker as it sort of moves around the edges of the graph using one of those labels, or we can keep track of, say, the heat value at each node using one of the labels there, so associating a value to each node that we look at. And so the examples here are all built sort of in terms of, you know, small grid graphs that we can look at. The assignments ask you sort of different ways to track through those and exchange those with other sort of either social network graphs or other types of graphs. So I'll just briefly, since we're sort of running down on time here, show you what the outputs are telling you for each of these and where the parameters are, so you can go back and tweak them on your own if you're interested. So for the first random walking example, we just have this nice grid graph, and what's just being shown here is sort of the path of the random walker. So at every step, it's moving from the node colored red to the node colored green. So it picked one of its neighbors, it moved down. Now at the next step, it was here at the previous step, it moves down into the corner, going to sort of bounce around back and forth for a little while. There's also a little bit of a script in the comments on one of these that shows you how to animate these into a GIF if you really like sort of watching the random walker bounce around on the nodes a little bit. Like I mentioned, what we're sort of really interested in is sort of the limiting behavior, this sort of steady state distribution here. And so this next one sort of takes a walk of, I guess, length 100,000 here, just records what nodes got visited along that walk. And then the plot is showing how often each node got visited. And so if you know a little bit of sort of Markov chain theory, the sort of steady state distribution for the simple random walk is proportional to the number of neighbors of each node. And so here, the node with the most neighbors got visited the most often. And this final sort of computation compares this sort of empirical example of just tracking the trace of an individual chain with what we actually expect to be the steady state from the eigenvector of the associated Markov chain process, and unsurprisingly, get the same result there. So for the heat diffusion example, we're again sort of working on a grid, parameter telling us sort of how many steps to simulate in the process, and then starting out with sort of all of the nodes having 0 temperature, and then setting a few of them to have some positive temperature and letting sort of the differential equation run. And so if we do that, then the output plots sort of show the heat diffusion over time. So here's our initial conditions. We set the temperatures of 4 of these nodes to be 10, and then we sort of watch as sort of the heat diffuses across the network slowly over time. And as you sort of adjust the number of steps and sort of make this longer and longer, eventually it does sort of approach the right sort of uniformly heat distributed steady state along the graph. I also included here, so this is one of those categories of things that's a little bit of a pain to do if you don't know how to sort of connect up the networks with the linear algebra. An example of how to do sort of spectral clustering using network X. So this is one of those, good examples of copy and pasting if you want to sort of try this on your own to start with. And so here's comparing sort of the initial club assignment to those sort of Laplacian eigenvector values, that should say, instead of eigenvalues, in each of the graphs, and the final partition that you get for both of those from doing the partitioning based on positive and negative elements in that vector. And then the final example here, and there's a lot more sort of documentation about all of the parameters at this link, sort of walks through simulating this process of having a SIR model evolve on a grid. So again, we start with some labels, some initially infected nodes. They can have some probability of infecting their neighbors at every time step. And then, after being infected for a while, each node has a probability of recovering in each time step. It sort of tracks the behavior of that. And so if you sort of play with those parameters a little bit, or play with the sort of the underlying topology, you can get a sense for some of the ways that this analysis actually gets used in practice to study these types of models. So I think I will stop there. And if we have any more questions, I can field those.
Yeah, so we have a couple, and I imagine more might come in, but can you say a word about what distinguishes Network X as a popular package for working with graphs and networks, and a couple of packages you like that may offer expanded or alternative functionality?
Yeah, so Network X is a really great starting point. Like, it's flexible, it's easy to use, has lots of sort of nice built-in information, and it also has this sort of nice documentation that helps understand why they made the choices they did in algorithm design. There are a couple of other different packages in Python that are focused around sort of more efficient implementations of some of the algorithms. So in particular, one of the things that we made a lot of use of here was this ability to have annotations, to have these sort of arbitrary labels on our nodes. But that can sort of slow down some of the algorithms that you're looking at if you're wanting to do some much larger computations. There's a couple of different packages under the various stages of development that work with those. There's also the nice sort of light graphs package for Julia, which is quite efficient, but again, doesn't sort of support the full range of arbitrary labelings. In the R programming language, there's, for example, the iGraph package, which is sort of similar to Network X. And over the last, I guess, maybe 2.5, 3 years, MATLAB has offered a bunch of additional support for actual graph objects and started to, take its sort of matrix first approach to graph analysis, but provide enough wrappers to sort of make it easy to do visualizations and make it easier to do some of these same kinds of things. That works at, again, a little more efficiently at a little larger scale, with the trade-off being that it's a little tougher to get started with, I think.
Next question. How do we get a dynamic graph? I mean, in the sense that the connections change by time steps. And it sounds like conceptually we are comfortable with how this might work, but in terms of implementation, how would you do this?
Yeah, that's a great question. And one that is easy to screw up if you approach it naively. Like we might want to sort of measure, like have one of these temporal graphs. We might want to have a sequence of graphs with, say, the same node labels, but we'd like to adjust the edges, capturing sort of different types of relationships or different statuses of relationships at different times, like the penguin example. And so so we can take our graph, and the sort of nicest way to do that, particularly if we have some like idea of just the perturbations, like we want to change a few nodes or a few edges, is to just make a new copy of the graph using just the dot copy function. So what graph names do I have floating around here? Very creative. So we can make the new copy of the graph G. And then we can start with that graph, and we can add edges to it, we can delete edges to it. And usually that sort of perturbation can be done using just those like add and remove edges that we looked at with the ego graph. If there's like a complete overhaul, like if we want this like sequence of Erdős-Rényi graphs drawn with the same parameters, but maybe some sort of consistency between the node labels, then we can just sort of build a list of those graphs and keep the node labels the same at every step. There also is support in NetworkX for, we only looked at sort of regular undirected graphs here, but for building sort of multi-graphs, building directed graphs sort of directly, just by sort of adding orientations to the edges or adding sort of multiple edges between copies of the same nodes.
Okay, and I think we probably have time for one more. Converting a series of plots into a GIF was briefly mentioned. Is there a tool that you recommend for doing this?
So I usually just use FFmpeg because it's usually installed automatically, and that's the code in the comments sort of provides you with the script for using that. There also are, if you're not making a ton of different files, then it's easy to, there are just sort of online services you can use to just upload the PNGs and get a GIF out that are free and easy to use. I should have mentioned, I guess the setup isn't in the code here, but I'll add that right as soon as we're done. So the nice way to do that is instead of displaying the plots like we have in the notebook here so we can look at them, you just use a plt.savefig, and then you can have all of the PNGs locally to sort of compile however you'd like.
All right, thanks so much for a great talk, Daryl. I will forward the remaining questions to Daryl if your question wasn't answered yet. And thank you everyone for coming. We have a short break and then we'll have the panel afterwards. So see you there soon.